happy to have Vivek back to tell us about perverse T structures.
Title is Perverse Microsheaves.
Oh, sure.
So yeah, thanks for inviting me. It's good to be back here. Let me just get started by stating some results, because at least the way the seminar used to go, you never know if you'll get to your results. Let's get started. So I want to state first an old result that I will not be talking about today, but to contrast with the new result. So there's a something I proved with John and Sheil, which is that a given a Weinstein manifold X, there's an inequality. So the wrapped Fukaya category of X is is the global sections of a sheaf of categories on the skeleton of X. And moreover, this sheaf of categories, it comes from a place that has nothing to do with the Fukaya category a priori. It comes from a subject called microsheaf theory. So we write that as the Fukaya category of X is isomorphic to microsheaves. Okay, and then that's the old theorem. This is the new theorem. And the new theorem is with Laurent Coates. I may have misremembered the accents that he has. Chris Quo, David Nadler, myself. And the new theorem says that, so what is a Weinstein manifold? Weinstein manifold is a certain kind of exact symplectic manifold. So where somehow, whenever you have an exact symplectic manifold, there's a one form that scales the symplectic form. And the word Weinstein, so the word Weinstein means two things. It means that this kind of thing is convex at infinity, this vector field points out. And it means that the skeleton, that's some kind of locus of points which don't escape under this flow. They somehow flow around under this flow. That this locus is Lagrangian. That's not actually the definition of what Weinstein means, but it basically means that. And so this new theorem, it's somehow this is about a real symplectic geometry. This side is a real symplectic geometry. And this side is about complex symplectic geometry. And whatever we prove in this paper, one consequence is the following. It's given a conic complex symplectic manifold okay, so I'll call it X. And some examples, things like moduli Higgs bundles, various symplectic resolutions. Conic means there's a C-star action which scales the symplectic form and somehow retracts it to compact locus. Then there exists a T structure. We'll discuss that, what that means maybe later. A T structure on category X, whose heart, so whatever a T structure is, it's something which allows you, it's something you put on a triangulated category, like Fukaya category, that's kind of infinity kind of thing, where the heart is an abelian category, the kind of thing you somehow learn about much earlier, whose heart is the global sections of a sheaf of abelian categories on CX. So I'll just write that as this Fukaya category of X heart equals new sheaf, this kind of microsheaves heart on CX. And moreover, the HOMs, so whenever you have a sheaf of categories, if you take two somehow local objects, the HOM space between them itself is a sheaf. And so, and moreover, this kind of sheaf HOM between two objects, F, G, and this kind of microsheaves heart. And this is a sheaf of abelian categories, but it's living inside some kind of sheaf of triangulated categories, and HOM, I think things in all degrees. And this and I shift it by some appropriate dimension. This is a perverse sheaf. So sometimes you'll see people use the word perverse sheaf of there's this thing called in mathematics called perverse Schober. Sometimes people informally call them perverse sheaves of categories for some complicated reason. But this is what, if someone just told you the word perverse sheaf of categories, that's what you would think it is. It's a sheaf of categories of which the HOMs are perverse sheaves. In other words, it's a sheaf of categories enriched in perverse sheaves. And so that's the kind of thing which this is. We'll discuss the details. Yeah, there's some hypotheses. I don't know any example which doesn't, so it's somehow.
There is a independent definition of Schober. Is this the Schober?
I mean, it doesn't even live in the same world as what, how to say, usually Schober, it means something on a one-dimensional space with some points. This is a sheaf of categories on some high dimensional, very singular space. I don't know. The only definition I've ever seen of Schober is this thing that lives on this. Maybe sometimes on an n-dimensional space with hyperplanar arrangement or something. But extremely limited class of spaces where I know what Schober means. Perverse sheaf of categories you can define on any singular space whatsoever. Actually, it's kind of interesting to think about somehow. This is one way you can make one perverse sheaf of categories, and you can ask, can you make any other ones? And well, you can push if you have a proper map with equidimensional fibers, and the push forward of a perverse sheaf of categories, the perverse sheaf of categories, and you can make a few similar constructions. But okay, so that's the statement. That's why I started with the statement.
You had a one-time manifold in the beginning, and then we know there's some a non-exact manifold. What's that?
I don't know anything about non-exact symplectic manifolds. Oh, I mean, that depends on your convention for perverse sheaves. How to say, you should shift this so that one lives in degree 0, right? I mean, if you have HOM FF, is going to be the unit, and that is going to be a local system in degree 0. And that I mean, so you need some shift here to allow it. It's like a shift by the dimension of the skeleton or something. Okay, and then maybe I just continue a little bit with this theorem, which is that some Maybe I should either impose that as an assumption. I think when you have this conic symplectic thing, it's always has to be Lagrangian, the skeleton, in this complex world. Certainly, every example is true, but and then so let me continue. So inside this, I didn't say exactly what this mu sheaf is, but so if I take now somehow bounded objects, so take pseudo perfect modules, pseudo perfect modules. This corresponds to asking if you have like a usual sheaf, asking if the stalks be perfect, like in the bounded derived category, and the stalks are somehow. So if I take this. This thing is a sheaf of Noetherian and Artinian, Artinian categories, so just like usual perverse sheaves. And the consequence of it being a sheaf of Noetherian and Artinian categories is that any somehow easy to construct stability conditions. Easy to construct Bridgeland stability conditions. Maybe I'll discuss that more at the end. There's time. I don't claim to know. I mean, I can make some. I don't claim to know what happens as you vary them. It's a quite interesting question. So that's just the statements, and now I'm going to take several steps back and then try and explain some of what these words mean and why they're true, and so on. Okay. So okay, so that's so I'm going to start now with a crash course in perverse sheaves. I guess before I embark on this, how do I pose this question? Is everyone an expert on perverse sheaves? No? Okay, so I'll give a crash course. So this won't really be a course in perverse sheaves. It'll be an explanation of why such a thing ever arises in the history of mathematics. So let's say X is a complex algebraic or analytic variety. And we have like O, X, analytic functions. And we take D some differential operator. Yeah, confusing. D is going to be the sheaf of differential operators, or maybe just the algebra. And I'm going to take a particular differential operator. And if you have a differential operator, you might want to ask, well, okay, let's look for f such that solve the differential equation. Hey, you might like to look for this. You might think about this. And then you realize that a good way to write this is you take Hom over D of this D mod PD, and then functions. Okay, because what is this? This is asking such a map is determined by where it sends 1. And P is some particular differential. It's such a map determined by where it sends 1. And if it's to be well defined here, wherever it sends 1 has to be something annihilated by P. Okay, so this is exactly things that solve that equation. And these days, there's no need to justify the next step, which is you take. I mean, this is now that's how like it's just. Oh yes, B. Sorry. There's no need to justify the next step, which is that I take now derived harm instead of harm. Okay, so that's somehow there's a long story about why you might ever do this, but let's just do it. Let's do it maybe in some examples. So the examples, let's take actually complex numbers. And that's why I'm writing it here. And I take the text of the complex numbers. Here are three differential operators. Okay, and like d dx, I can take just multiplication by x, and I can take x d dx minus alpha. And so so this is p. And then, okay, what are the solutions? Well, here we have constants. And here, there's no solutions in the ordinary sense. There's no function of which x times that function is 0, except maybe a 0 function. And okay, how about this? Well, this one, the solution, some kind of solution in the classical sense is x to the alpha. Let's see, did I get that right? d dx is alpha x to the alpha minus 1. Yeah, I think so. Yeah. So, but pay attention. This thing, it's first of all well defined, maybe away from 0, and it's whatever you think about what it is. It's the kind of solution form. If you go around 0, there's a monodrome. You come back to yourself. And so this is harm. Yeah, I'll have to compute x. So we should compute harm. We should do what? We should resolve this d mod PD. So this d mod PD. Well, we can write that. We can resolve it. It's d and p. And so now we should compute harm from this. And what is harm from this into O? Well, so then we have O, P, okay? And we should take the cohomology of this complex. And so this is H0, after H1. And if P is d dx, well, d dx is surjective, so this is 0. And if P is x, well, the co-kernel of that is the skyscraper sheaf. How to say and the skyscraper sheaf at the origin. And maybe that's not right. Oh, it's the skyscraper sheaf at the origin. And then this one. Some exercise to show that it's 0. Okay, so what was the point of me going through this kind of exercise? Yeah, alpha is not an integer. So what was the point of me going through this kind of exercise in freshman calculus? You observe that here you have a sheaf living, which is in fact a locally constant sheaf living in degree 0. You observe here, you have a skyscraper sheaf living in degree 1. And here again, you have a locally constant sheaf living in degree 0. Okay, and so if you are Kashiwara, you immediately generalize this to the definition of perverse sheaves. Maybe this one I want to keep. So it's historically motivated in part by that kind of calculation.
Previous example.
What? What?
Why in each one this thing is
Let's put it back. We have O, d dx, O. Oh,
okay. Okay.
okay. I guess there's more than one reason I went through this exercise. I mean, I haven't written any statements yet. Okay, so where's this? The definition, which is that a constructible sheaf F is perverse, and sheaf always means complex of sheaves. Perverse if I take its ith, its jth cohomology sheaf, H, J, F is supported in codimension these J, and the same for the Verdier dual of F. Yeah, that's the definition of perverse. And the theorem of Kashiwara is that if P is a holonomic D-module, maybe I shouldn't call it P anymore, holonomic D-module, then this is hom D analytic is perverse. So there's just you know, like the first time you see this definition, there's some shift. Okay, I don't put the correction. The first time you see this definition, you may wonder where on earth this comes from. There's one place it comes from, and there's a even better theorem, which is the Kashiwara and Kashiwara and Mabkut. And this even better theorem says that the space of holonomic D-modules is equivalent, somehow a regular holonomic is equivalent to the space that this category equivalent to category of perverse sheaves. I haven't said what the word regular means. It's irrelevant to this talk, but some further restriction. So I mean, just to say that this is really incredible theorem. It tells you that D module is some complicated thing. It involves thinking about solutions of differential equations. A perverse sheaf, it's a very simple thing. It's a topological in nature. And so it means that if you take something which somehow described on strata in a locally constant way, you can recover some differential equation uniquely of which that's the solution. Okay, so that's and
Hold on, D models are pretty nice. Why is it the same? Why is it true? He said something.
I should give a whole course to explain this.
There's no.
No. This is important. I mean, it's
No, I mean,
it's
if you didn't tell us about the theorem, that the first definition is not really weird.
that's correct. Yeah. I mean, this is not infinitely hard. I mean, this in some sense, I don't know exactly how Kashiwara's proof went, but you could imagine that you apply resolution of singularities and you essentially reduce it to this calculation. Okay. What? Yeah, very. Okay, so there's some operation on sheaves called Verdier duality. On a manifold, it's basically Hammond to constant sheaf on a manifold. Okay, so that was to explain why you might ever want to think about perverse sheaves. And I'll just say in words that there's a version. I mean, D module is something that lives on a manifold, on a complex manifold, but there's what's called microlocalization of it, which lives in cotangent bundle, and you can make a version of this microlocalization which lives on any contact manifold. So Kashiwara constructs a sheaf of categories in a contact manifold, which is locally the microlocalization of D modules. And the related version of that provides you some categories you can associate to things like symplectic resolutions and conic symplectic manifolds. And these are the items, if you've looked in these papers of Kashiwara-Rukier or Ryden, Proudfoot, Licata, Webster, that provide those categories. And you could ask, is there some kind of Riemann-Hilbert correspondence for those things? If you feed that in, is there something of the nature of something like constructible sheaf category that you'll get out? And the point of this is it provides a candidate for the answer. Almost certainly it is the answer, and at least somehow it's a thing of the right nature. Yeah.
This kind of midpoint where X is potential bundle or something.
Sure, yeah.
That theory becomes really easy in that case? Or
I mean, yeah, if you
that would be like the closest.
I mean, this theorem becomes, how to say, when this X is cotangent bundle something compact, then as I've written it, the CX is just zero section. And yeah, in that case, this theorem contains very little content. But you could put maybe a slightly more general version of it where you don't demand that the CX is just the zero section. And you replace wrapped Fukaya category with some partially wrapped Fukaya category. And in that case, it has as much content as the somehow full statement, basically. Although you could have proved it without the things I'm about to say. Okay, so okay, so that's
How strong is the theorem? Does it actually follow,
I
or
don't
does it
know.
have
I mean,
I think for these
yeah.
in this set,
Uh,
Fukaya exceptions follow like there's not just there's some C structure, but there's a T structure who where then morphisms are just like in degree 0.
but that,
Associated all.
that's false.
I think in some generalities it's true.
Sorry. I don't promise you that there's no T structure for which that's true, but for this T structure, it's false.
I would think okay.
Yeah, wrapped. Yeah. Oh, this handle. I mean, the harm will be in degree 0 when you have two smooth Lagrangians with smooth intersection. Because what this theorem promises you is that the harm is a perverse sheaf. But if the intersection is something more complicated, then you have no right to expect. Or in fact, maybe if it's a single point. If you have smooth Lagrangians intersecting a single point, or in many points, then harm lives in degree 0. That's a consequence or ingredient of this theorem. But the moment they intersect at something of positive dimension, then it's not true. It could be. Okay, so now I want to explain a little bit about how you arrive at the proof of this theorem. Okay, so now I should explain about the microsheaf theorem. So we go back now to real geometry. So M is a real manifold. And I look inside T star M. And I take a sheaf, F is a sheaf on M. Then I get some locus called the microsupport of F inside this thing, and it's defined as follows. This is the maybe just I'll define it informally. This is how the locus of directions along which sections do not change. That's some kind of informal definition, and you could turn it into a precise statement. But whatever it is, it's some kind of conical subset of the cotangent bundle. And if your sheaf is locally constant, then this conical subset will be just the 0 section. If your sheaf is constructible, your conical subset will be contained in the union of conormals to the strata. And this subject, it's developed by Kashiwara and Shapira. They write some book on it. You can try and learn the subject from there. Now I want to define a sheaf of categories on the cotangent bundle. And this sheaf of categories, well, to define a sheaf, you should define a free sheaf and then sheafify. So I tell you what the free sheaf is. Well, you take all sheaves on the manifold. And you divide by sheaves whose microsport is away from omega. So so this is some sheaf categories. And now so this is about cotangent bundles, and I should explain how to, to get something like this theorem, I should explain to you how to associate such a thing to things that are not cotangent bundles. And the way is you just put them in a cotangent bundle. So if V is a contact manifold, then you take V and you embed it in some maybe some close-sphere bundle of some very large guy. And you might think, okay, well, I have this category of microsheaves, the sheaf of categories defined on cotangent bundle. Maybe I just restrict it. So your first attempt, you might say, okay, I take microsheaves, and I take microsheaves, let's say, supported in V. But this is not such a good idea because you get 0. Okay, so you shouldn't do this. And the reason you get 0 is that always when you take microsheaves supported, the support of a microsheaf is always something coisotropic. And if you take a high codimension embedding of a contact manifold, which is some kind of contact embedding, it will definitely not be coisotropic. And so what you in fact do is you have to thicken this embedding. So you have this V, it sits inside this closed sphere bundle. And it's a contact manifold and a contact manifold, and so its normal bundle has a canonical symplectic structure. So you have this new V symplectic normal bundle. And for now, let's choose a Lagrangian inside there. So it's a half-dimensional subspace. So choose inside here. Polarization. But usually polarization is inside tangent bundle. And there's some kind of. Oh yeah, this is polarization. Yeah, this is polarization. So you choose this thing. And then you can take microsheaves. So the neighborhood of V, it looks like this new V, and so I can thicken in the direction of this LV. So I take microsheaves supported along. I'll just write LV, and this is some kind of sheaf of categories, and I'm going to call this microsheaves on V. Okay.
Sorry, the symplectic normal bundle is not just the normal bundle.
It's just the normal bundle, but it carries a symplectic. It is a symplectic bundle. If you have like a symplectic manifold, then a symplectic manifold, then the normal bundle is symplectic, and same for contact manifold and contact manifold. So you have this sheaf of categories, and you can ask on what did it depend. I embedded this somewhere. I chose some embedding. I chose this Lagrangian, and there's the theorem of Gromov, which says that any two such embeddings, they're isotopic to each other. You take n big enough, and not only are they isotopic, the space of such isotopies becomes arbitrarily connected as n goes to infinity. And one shows that this microsheaves somehow locally constant along such isotopies. So it doesn't depend on the embedding. But it does depend on this Lagrangian, on somehow the isotopy class of this Lagrangian. So then we can discuss in what way it depends. Which guy? This one?
Yeah.
Maybe let's repeat about this guy first. So this guy was a sheaf of categories who lived here. And its definition was I take, all sheaves on, I should give you first pre-sheaf of categories. To give you this pre-sheaf, I should tell you what it assigns to an open set. And what it assigns to an open set is I take all sheaves on Rn, and I quotient that by sheaves whose micro support stays away from that open set. So just the things that only care locally about this stuff. And okay, what is this? Well, now I take objects whose support lives inside this LV. And that's a sheaf of categories on LV, and I pull it back to V. So I should restrict this to V. I just write this. I mean, somehow, I write this, for example, to contrast with how complicated it is to define Fukaya category. This I've more or less told you the complete definition of this item. Okay, so but I mean I owe some discussion of how it depends on this. And so we have this V, and it's a contact manifold, so it has a contact distribution, which is some symplectic vector bundle classified by some map to BU. And then let's go to the somehow classifying space of Lagrangian Grassmannians. So this BU, I took n very big, so I've gone to the stable BU. And then here, and this Lagrangian L, this polarization L, it's the same as a null homotopy of this composition. BU is the classifying space of stable symplectic vector bundles. This somehow limits as BUN. So n goes to infinity. And limit, if you have a given symplectic vector bundle, you can add a trivial one, and this gives maps from BUN to this thing. And this is just corresponding stable Lagrangian Grassmannian. And what does it mean to give this kind of polarization? It means that it means this. What? What? You don't like this B? I mean, this is the Lagrangian Grassmannian. And if I want to form the Lagrangian Grassmannian bundle of my symplectic vector bundle, it should be classified by a map to the classifying space of Lagrangian Grassmannian bundles. So maybe you're concerned because you don't think U mod O is a group, but it is. UN mod ON is not a group, but when you go n to infinity, it becomes a group. So this thing, and in fact, it doesn't. It depends on less than this. So what I explained so far, it looks like this microsheaves depends on the choice of a null homotopy of this composition, but in fact, it does not. I mean, it depends on less. And so the theorem, which some part of this theorem is due to somehow David Nadler and myself, and some part, but really we somehow just set up some machinery so that we can invoke a somehow old calculation of Stéphane Guillemot. The theorem is that in fact there's a further universal map. B2 pick of whatever category coefficients you're using. I'll explain what this means in 1 second. And what you actually need is a null homotopy like this. So the theorem is that as mu sheaves V can be defined using and only depends on so a null homotopy of V to pick. This is some universal map. So let me explain what is this V2 pixie, and so here this is the first time we met this C, and C is my category of coefficients. So C is some stable, presentable. We ignore these words, we don't know what they mean. Symmetric monoidal category. And the only one, the only such category, which is so I mean, you can choose any, but so for example, e.g. DGZ modules. And so what is pixie? Pixie is it's like C linear. We'll just say so. It is invertible objects. Invertible objects. So this is what it would be if we were not working in this infinity world. The statement that's literally true is this. And so I'm just going to give you an example of this pixie. Maybe that'll make this pick Z mod under this monoidal structure. It has you tensor it by someone and you get one. So pick Z mod. Well, it's so you might think there's only a unique invertible Z module. One. Well, let's first compute this pi 0. So definitely in here, there's the Z module Z. But it's DGZ modules, so there's this thing with some arbitrary shift. So this thing is just integers. It's like Z with some shift. And let's pick Z. And what this thing actually is, it's Z plus something else, and this is somehow the homotopical part, which corresponds to automorphisms of the identity functor, and those are automorphisms of the identity functor of Z modules just plus minus 1. Okay, so that's what it is. And so whatever this map is, in this case, some map from V to this B to B to Z plus B3 Z star, and some kind of I guess this theorem, as I stated it, has nothing to do with Guillermo. It's just somehow a general fact. And then the theorem of Guillermo is that the theorem that null and null homotopies of this map is the same as the data usually used to define Fukaya category. I mean, he computes this map, or more precisely, that map mu. The data usually used to define. What? Yeah. What?
You have some pretext. You said it's there's some kind of clue.
Yeah.
There's something depends on some kind of data.
Yeah. I haven't.
I don't even know what that data is about.
I'm about to explain.
Okay.
Yeah, I'm about to explain. I mean, you should have already been concerned when I stated that theorem, because Fukaya category, you need to choose some data to define it. You need to choose somehow grading on your symplectic manifold, which is this like trivialization of twice the Turing class. And you also need to choose its background class. And so what this theorem says is that this map, what such a null homotopy is a grading and a choice of background class. Usually it's described as an element of H2X in Z2. And the point is that what this theorem says about this piece is that the map's trivial. I mean, this map is canonically zero, the second part. And so it's rather than just being a torsor for H2, it's actually isomorphic, canonically isomorphic for H2. And then this part about this first part, what it translates to is that this map U mod O, if you d-loop, this map U mod O to B2 to B Z, and what is BZ? BZ is S1. That this map is the determinant squared. That's what that theorem says. And then, I mean, that's the same as this kind of business. Okay, so that's and that's what you would need to choose ordinarily. And the point is that if you if there's a complex symplectic manifold, then this map, it factors through, it's like B complex Lagrangian cross model. And this is simply connected. And so the somehow zeroth part, I mean, this is simply connected. And so this like zeroth part is canonically null homotopy. That's why there's no such information. It's kind of a long story about like what. Anyway, that's somehow the point. That yeah. I mean, just in terms of.
You just phrase it as existence of actual given that data, just give the polarization of your
I mean, a polarization is null homotopy of this map, and not. I mean, in general, like how to say, this. The simple connectedness of this means that like this pi zero part is canonically zero here, but it certainly doesn't mean that this part is null homotopy.
It reminds me if I have a symplectic manifold, what's the manifold?
If it's exact symplectic manifold, you multiply by R. Lambda plus dt. Yeah, so yeah, I think that's almost what I wanted to say. So I guess what this explains so far. So what I've explained so far is how to pick this information. I'm supposed to take some kind of break, right? Actually, do we stop after an hour now, or what? 2 hours is the usual. Yeah, okay. No. Yeah, it's no.
If you feel like you want to break.
No, it's okay. I can continue. Yeah, okay. So this was about some kind of discussion of background classes and so on. And now I should explain to you where this kind of T structure comes from. So now let's say I have a Legendrian. So I'll NV some Legendrian. Then I have two, and let's say I've chosen, so I have this V to this B2 pick, and I've chosen some null homotopy. Okay, so I've chosen this data. I have L sub Legendrian, and a neighborhood of a Legendrian always looks like its jet bundle. And the jet bundle, it comes with a canonical polarization. And so, on J1L, you have a canonical, not just all the way to this B2 pick. You have a canonical this V, this L to B U mod O. It's about 0. Because you can always take the direction of the Legendrian itself. And so on this J1L, you have a category of microsheaves, a sheaf of categories of microsheaves defined by mu, and you have the sheaf of categories of microsheaves defined by this stupid thing. And so it means that if I take sections along L of microsheaves on V, then I want to know I want an identification with sections with local systems on L. This is a sheet of categories, but with local systems on L. And the statement is that the statement is that a homotopy of let's give this null homotopy a name. I call it this is nu L. A homotopy from nu L to this mu restricted to L induces such an isomorphism. This is not an additional statement. This follows from what I've already told you, because I've already told you that this kind of choice of this data uniquely up to contractible choice determines that microsheaf category. And so now I've given you two different such choices of data. And so if I give you a homotopy between them, then I had better, then you get equivalence of these categories. And so now you start to see where I'm going to try and produce a T structure from, because this carries a T structure. It's just local systems on the Lagrangian. And so we can discuss local systems in degree 0. And the question now becomes, how do I, in an organized way, at least to give a candidate for what I want the T structure to be, how do I, in an organized way, produce these homotopies? But I mean, what it will give me is it'll give me a family of, it'll give me a sheaf of categories on V time, on L now, on L times I, which is constant, locally constant in the I direction. Yeah, I don't. I mean, it's not good to work with triangulated categories. They'll be like DG categories or something. Yeah, it's like sheaf of DG categories.
Somehow control the boundary.
I mean, I'm just going to. I'm going to define the heart. I mean, how to say what if I fix the homotopy, then I have an isomorphism, and so I can say, well, I know what the heart is here. I'm just going to go send it over there. But then you have to face the question of how do you produce a canonical homotopy, a canonical choice of homotopies. No, I have no idea how to think about this question. It's a good question. I have no idea how to think about it.
So before you have the up to now, say there's a canonical map to be.
No, I mean the map to be, if you want, this canonical null homotopy. I mean, the map to be, if you want, is what it was before, just restricted from V. The point is just that like on a cotangent bundle is a canonical polarization by like the fiber or by the tangent to the thing itself. So and polarization is the same as the null homotopy of the map to V of U mod.
You said something about the tangent direction. I thought this is like.
Yeah. All right. So U mod O is a group, and so is B of U mod O. And -1, I mean, it's not the inverse of that group exchanges the map that classifies the tangent and the map that classifies the normal. And somehow like normal polarizations turn into tangent polarizations by this map. Okay, so yeah, so we have this homotopy. I mean, given such a homotopy, we get such an identity. And so what I owe you is to explain how uniformly I'm going to produce such homotopies at every point. Of course, that will just produce a candidate, because this is true. I should have said this is for smooth Legendres. Smooth Legendres. And so the way I'm going to define, I'm going to ask what the T structure is. I'm going to say that my T structure, it's that some smooth Legendrians every smooth Legendrian in the skeleton, I ask that my object somehow sent across some map by some homotopy I haven't yet told you how to produce is a degree 0 local system. It's not obvious that it will be a T structure. But once I've made that somehow definition, then I have something which I can check locally. So it's a not difficult fact that on a sheaf of categories, you can make a T structure by making a sheaf of T structures. And so I have something to check locally, and then locally I can go into some cotangent bundle and just do sheaf theory. So the main task is to produce a candidate which is local. It doesn't matter. I mean, I either would give you a T structure. Like you always shift a T structure. So okay, so how it's why does it exist? Well, it's the same as before. That somehow this thing is simply connected. So maybe one way to say it is that this So the point is that let me take some looping. Okay, so if I go around or somehow loop in this if I loop twice, then the situation is as I go around the skeleton, I come back to my same category, but some automorphism has happened. That automorphism is tensored by some object of this pixie. In particular, the grading could have shifted. And the thing I have to exclude is the possibility that there's grading shifts. And the point is that if this map factors through here, this space is connected. So the image of this is the connected component of the identity here. So therefore the grading can't change. That's the that's basically all there is to say. Maybe it's worth saying that the point of this discussion was to explain that this condition could be made local and sheaf theoretic, and then you can check locally. But now that I've explained this in this enormously complicated way, to say what the T structure is in terms of the Fukaya category is actually quite easy. So now I can translate that into a prescription about what this heart of the Fukaya category is. So I remind you that when I have this kind of thing, this is generated by cocores. Let's call them C alpha. And these are disks. And if you, as I mentioned, to define the Fukaya category, you have to put what's called grading on your symplectic manifold, which is this trivialization of twice the Chern class. And then to give an object there, you're supposed to give a Lagrangian plus a lift of that Lagrangian to the fiber-wise universal cover of the Lagrangian-Grassmannian bundle. But when the Lagrangian is complex, since you're lifting it to the complex Lagrangian-Grassmannian bundle necessarily, and that's simply connected, so you have X, and over X you have LGR X, and you have LGR X tilde. Okay, this Lagrangian-Grassmannian bundle is fiber-wise universal cover. And then if X is complex, and we discuss complex Lagrangians, there's LGR CX, and that maps here. But this thing has a canonical lift there because it's simply connected. Right? I mean, the fibers of this simply connected, that's universal cover, so it has canonical lift. And therefore, if you have a complex Lagrangian, it carries a canonical grading. And in particular, these cocores, they're not complex, but they're disks, and at one point they're transverse to a complex Lagrangian, so they may as well be complex. I mean, for homotopical purposes, they may as well be complex. This is a canonical way to give them a grading. And so this heart, you translate it, it's a HOM where this C alpha L is in degree 0. I don't know if that's true, but it's not relevant. I mean, to give that might be true, but to give a grading, it's a homotopical issue. And I mean, this cocore, here's the skeleton, and cocore is transverse to the skeleton. And so at this point, somehow it's canonically homotopic to a complex Lagrangian. And so it has a canonical grading for this reason. Okay, so this, maybe I should have began with this. This is a description of the heart. But as far as I know, no one has any idea how to prove directly that this is an abelian category. And the point of this long discussion was that in this microsheaf world, I can make this condition, like described. Yeah, yeah.
So you said this card,
Yeah.
what's the statement?
Uh,
That they have a property that belongs to the.
No, this thing is generated by cocores. And now it's a fact that when I translate this discussion with this equivalence of microsheaves, that the resulting heart is characterized in this way. It's the objects where Hom from the cocore lives in degree 0. But how you would ever prove that, for example, how you would ever prove that this is an abelian category, what kind of thing do you have to prove? You have to prove, for instance, that this is closed under extensions. And that's in terms of holomorphic curves, some quite complicated condition. But if you translate to sheaves, you find some condition which you can check locally, and locally you reduce to cotangent bundles, and cotangent bundles is essentially classical. That's the,
In fact, in our world, all the humps between them are exactly degree 0 between.
yeah, it could be. Yeah, I mean, but it's not generally true.
No, it's very, very special for one.
No, but so for example, consider T star S2. That's as holomorphic symplectic as you want, and take the fiber, cotangent fiber. Endomorphisms of the cotangent fibers. No, but that's a cocore. I mean, that's what it's cocore. I mean,
No, actually, it's a fine bar, yes.
I mean, you won't find anyone else who generates that category.
Yeah,
But better take this one. And its endomorphisms do not live in degree 0.
Okay, so something's wrong with that. So there you have to put some stops, something probably to make it.
Oh yeah. If you put appropriate stops, then you can ensure this guy endomorphism degree 0. But in general, maybe I'll stop there. Oh, I was supposed to say about stability conditions. So, I mean, let me just remark about stability conditions, which is that you check locally that maybe I won't. Okay, fine. So the point is that in this setting, that there's a kind of characteristic cycle map, which goes from this Fukaya category to somehow H, the appropriate dimension of X, but of the core of X. And because this thing somehow locally can be described as perverse sheaf categories, it takes this kind of Fukaya X heart to positive linear combinations of cycles. Cycles. And so if you take any, and what is a stability condition? It's a T structure plus some map from this Grothendieck group to C with some positivity property. And so if you take any if you take any somehow, if you take any function, what? No, not turn character, characteristic cycle. goes with positive linear combination of cycles. So you want this kind of function and satisfying some properties. And what properties it have to satisfy? It has to take the heart to the upper half plane. And that's trivial to ensure if you know this. I guess I should have said this thing. It's this math factors through the group. So you take any function to C, which is positive on this positive. It's in the upper half plane on this positive to cone. Many such exist. And then you need to know. So it's the data of T structure, and this kind of function satisfying some conditions. This what is it called? This Harder-Narasimhan condition. But Harder-Narasimhan condition, it's kind of automatic on abelian and Noetherian category, because whatever it's about not having any infinite decreasing chains of things of smaller and smaller slopes. There's no infinite decreasing chains at all. So yeah. But what I don't know is take some example. Here I phrase things in terms of Fukaya category, just somehow for flavor. But really, it's something you can define for any complex singular Legendrian or complex conic Lagrangian. Yeah. So for instance. What I don't know is here I can make somehow like one chamber in this, like one kind of chart in the space of stability conditions, but you can then start moving this function so that this it stops being positive on this thing, and well, Bridgeland promises you that the stability condition can be continued, but you're going to have to then change the T structure, and I don't know what it changes to. I think the answer must be related to this Bezhev-Khovnikov business, but yeah, but I mean, this is on the A side. This is like somehow same space. It's like same space, but also this is like not equivariant. It's